Welcome! Today we will explore k-means clustering, an essential method in unsupervised data mining. The primary goal of k-means clustering is to divide a dataset into k non-overlapping clusters, where each cluster is as homogeneous as possible. Let's get started. The number of clusters k must be specified before starting the analysis. While this value can be informed by prior knowledge or domain expertise, experimentation is often necessary to find the most meaningful number of clusters. Hierarchical clustering methods can also help determine the appropriate value for k. The process is iterative. Observations are assigned and reassigned to clusters based on their proximity to cluster centers. Let's explore how this process works. The k-means algorithm begins by identifying the initial cluster centers. A common approach is to randomly select k observations from the dataset as the starting cluster centers. From there, each remaining observation is assigned to the nearest cluster center, forming the initial clusters. The algorithm calculates the cluster centroids, or the means of the variables within each cluster, and uses them as the new cluster centers. Observations are then reassigned to their nearest updated cluster centers. This process of recalculating centroids and reassigning observations continues until no significant changes occur. The reassignment and recalculation steps aim to minimize within-cluster dispersion, which is measured as the average Euclidean distance of observations from their cluster centroids. The algorithm iterates through the following steps: reassigning observations to the nearest cluster based on updated centroids, recalculating the cluster centroids to reflect the new cluster assignments. This process continues until convergence is achieved, when cluster dispersion can no longer be improved. It's important to note that k-means clustering relies on Euclidean distance as a similarity measure and therefore requires numerical data. Categorical variables must be transformed into numerical form before analysis. Let's summarize the steps involved in k-means clustering. Specify the number of clusters k. Randomly select k observations as initial cluster centers. Assign each observation to the nearest cluster center. Calculate the cluster centroids based on current assignments. Reassign observations to clusters with the nearest centroids. Repeat steps 4 and 5 until no further improvement in within-cluster dispersion is possible. This iterative approach ensures that the clusters formed are as homogeneous as possible. K-means clustering is often preferred for its computational efficiency, especially when working with large datasets. Compared to hierarchical clustering, which requires calculating distances between every pair of observations, k-means only calculates distances between observations and their cluster centroids, making it significantly faster. However, there are some drawbacks. The results of k-means are highly sensitive to the initial choice of cluster centers, which are selected randomly. This randomness can lead to different results across runs. To mitigate this, multiple iterations of the algorithm can be performed, and the best result can be chosen. In summary, k-means clustering is a powerful and efficient method for grouping numerical data into meaningful clusters. Its iterative approach ensures clusters are refined to minimize within-cluster dispersion, and its computational efficiency makes it a practical choice for large datasets. However, the algorithm's reliance on the initial selection of cluster centers introduces some variability in results. It's essential to combine k-means clustering with careful evaluation to ensure reliable and meaningful outcomes. Let's look at an example using JASP. Upload the same cities file that we used for hierarchical clustering in Part 1. Select the neighborhood-based option under Clustering in the Machine Learning tab. Drag the crime, poverty, and income variables into the Variables box. Then select the appropriate options for tables and parameters as presented here. Let's take a look at the results and compare them against the hierarchical cluster example. The silhouette score, which is a measure of how well the data points in one cluster are separated from other clusters. A higher score is better. The scores for each clustering approach are very similar with only a 0.02 difference. When we look at the cluster means for each approach, we have a city cluster that has the lowest crime, lowest poverty, and highest income when compared against the other two clusters. While the cluster means are different for the two approaches, the clusters are similar in characteristics across the two approaches. This concludes our session on k-means clustering. Thank you for your attention.